All right. Can you hear me? Yes, good. All right. So this is part 3, and we're going to talk about um, things that are not single polymer in solution bulk phase. Right? We're going to talk about what looks a lot more like biological systems. And the key idea here is complexity and how condensates interact with one another and their environment. Okay. So okay, complexity and interfaces. Going to have a couple of vignettes. Can't go into an enormous amount of detail on any of these, but I want to give you an overview of what people are thinking about in terms of how phase separation and some of the polymer physics concepts that I've been telling you about for the last 2 days can actually lead to interesting and biologically useful forms of self-organization. All right, so the first question that I want to spend some time thinking about is, how do we think about high-dimensional concentration spaces? Right. So, okay, so how do we think about many components? And so specifically, we want to think about what happens not just with, say, 2 polymers in solvent, some of the things I sketched last time, but really in the regime where we have many, many more uh, molecular species than just 1 or 2, right? So we really want to go in the direction of n goes to infinity. All right. Okay, so this problem is obviously complex. A reasonable starting place, though, is to think about, again, stability in multi-component systems. And so I'll just write down the expression that we had last time for the condition to have a stable phase in a multi-component system if we assume the Flory-Huggins model. So this is our stability condition, and this matrix must always be positive definite, right? So just as a reminder, these are our, this is the Hessian matrix of the free energy. Our rows are the concentrations of the polymers, and the L's are the different polymer lengths. We've multiplied through by a factor of L to make everything look nice and symmetric. And this thing here is the overall interactions between 2 different polymers. Right? Yes? Yes. Right. Great question. So it's hard to give just a single answer to that, right? So it is a model. It has significant limitations. Right? So just say what it is. This is Flory-Huggins. Right? The idea that a monomer, when we think back to the original derivation and inserting a chain into a condensed phase, this mean field approximation becomes better when a monomer can't distinguish a monomer on a different chain from a monomer on its own chain. So as long as the condensed phase is condensed enough, there should be lots of monomer-monomer contacts. There's actually a very nice way of quantifying this in polymer physics. Talk about an overlap parameter, which is basically how many contacts a single polymer makes. with other, how many distinct chains it interacts with simultaneously. And if that number is really, really big, then this sort of averaging that's inherent in this mean field model works reasonably well. So long chains, condensed systems, and where the monomers are not too different from each other, this should work reasonably well. But it's, of course, just a starting point. And in fact, we're going to violate one of those assumptions just for mathematical convenience. Let's make two simplifying assumptions, which are not necessary in general, absolutely not if you wish to do numerics, but are very useful for making a qualitative picture without any complex math, right? So the first simplifying assumption we're going to make is that we're going to assume that all of our various polymer species exist at equal concentrations in the overall mixture. Right? So it's obviously not true in biology, but we will do this anyway. Again, just for convenience, right? So for every species I from 1 to n, we assume that it has this that the concentration is just some average concentration. Right? And then the second thing we're going to do is assume that the overall concentration, or sorry, overall volume fraction is still not so large. And the reason we do this is, again, just purely for convenience here. It's not necessary. Yes? Right. So this one comes from the ideal contribution to the chemical potential. And this one comes from the excluded volume of monomers taking up space. It diverges if you have a total volume fraction going to 1. Right. All right. Okay. So while these are two, very, very extreme assumptions, if we use them, then our stability condition becomes this. We can then write this equation. So this thing here just says that we have an identity matrix, right? And then we have this scaled interaction matrix here, which is all of our pairwise interactions. And this is a reasonable description of stability as long as we are at relatively low polymer concentrations, which can indeed be in a condensed phase if we have very long polymers. Yes? Right. So it's I believe the question is, what exactly do we mean by the stability condition here? Right? Why so we're saying that I'm writing it this way. This means that that it's positive definite. Here's a curve. The matrix is positive definite, right? I'm just writing it out this way so you can see, but I think it's that this one is perhaps a bit more natural. I got rid of it by making this assumption here. You don't have to do that. You can end up moving it over in here, and then it becomes a constant. And it's not, so yes, yeah, sorry. I guess we lost a term here. Right, so it should be -1, right? Yeah. Thanks for pointing that out. Right. So this is the thing we care about. Right. So we have some rescaled energies here, and we have our contribution from the ideal part. Yes. Yes. Minus LILJ. Right. Thanks. Good. Okay. So here's what we have. And we want to say what kinds of instabilities could we potentially get in a system like this? The problem is that we don't know what these interactions are. So what do physicists do when you don't know what type of interactions to use in a really complex system? You make them random variables. Right? So we can do that. We can make an assumption that we know something about the statistical properties of the interactions among all the different polymer chains in our system, and hope that we can take advantage of this large number of component limit to actually get results that self-average, right? So that as n becomes large, our predictions actually become a bit more certain. Okay. All right, so we're going to make the assumption that these rescaled elements of this symmetric matrix here are random variables with some mean B, some standard deviation sigma, and everything will be chosen identically distributed, right? So again, it's a symmetric matrix. So if you choose epsilon ij, that also fixes epsilon ji, right? But other than that, we assume that all of the polymer-polymer interactions are independent. So it's really the simplest thing you can possibly assume. And if you do that, then you can sketch out immediately what the sorts of instabilities you could get in a system like this. Okay. So what we care about is the eigenspectrum of this matrix, right? And it turns out that if you have these conditions here, then in the limit that you have a very large number of distinct components, this spectrum converges to one of two possible forms. One looks like this, right? So we have our eigenvalues, lambda. And if we assume that the mean of the matrix is very negative compared to a rescaled standard deviation, should look something like a central limit theorem, then you get two different types of eigenvalues. You get one that exists down here, and then everything else exists in this semicircle. So this is a continuous density of eigenvalues, and this is a lone eigenvalue here. So there's just one, and here we have n minus one. This thing occurs at approximately n times b, which means that we're just adding up all of the interactions in our system. And the associated eigenvector looks like just all ones. Right? Whereas everything in here, you necessarily have orthogonal eigenvectors. So this spectrum goes from minus to plus 2 sigma into the 1/2. Okay. So that's what this looks like. And if you have this other condition, other case, then the only difference is that you no longer have that lone eigenvalue. You have this. Yes, yes. There's a third case if B becomes very large, but I'm not going to care about that one because we are interested in instabilities, and instabilities occur when you have negative eigenvalues, right? And so we only care about the left edge of this thing, and so there are only 2 possibilities in that case. Right? What this condition means? So what it means is that when something's unstable, it means if you have a very small fluctuation in concentrations, then the system demixes in that direction, right? So in other words, if I locally have a slight increase of one or say a linear combination of different polymer concentrations, which means elsewhere in the system you have a slight decrease, then that gets amplified and the system demixes and you end up with different phases, right? So this is a sufficient condition to get phase separation. It's not a necessary one, but this is something that you can just very easily reason what the sort of geometry of the space looks like. Yes, exactly. So this is the condition for spinodal decomposition. The condition is that this whole thing must be positive definite. This thing must be positive definite in order for the mixture to be stable, right? Where we have imposed some average concentrations in the system. We aren't saying anything about this matrix except these conditions here, which are just assumptions in order to be able to make some predictions. These are, so the conditions, the positive definite condition is for the matrix as a whole. Yeah. Yes. Epsilons are the interactions, yes. Why do I make these the random variables? Because the epsilons describe the interactions between the various polymers in the system. I don't know what those should be necessarily without a huge amount of data. So a reasonable place to start is just to say that you only know something about the statistics. And this is the simplest thing you can do, obviously, right? You can say that actually I assume there's structure in the matrix, right? I assume that not everything is uncorrelated, right? Like different polymers interact in similar ways. You can put in all those things, and people are doing this now and coming up with more and more complex predictions. I think I saw a hand here first.
Epsilon is a kind of variable. Is there any way to guarantee that it satisfies that criteria? The positive definite criteria?
I'll come back to that in just 1 second. I think I can show that just graphically. Yes.
Yes. So this is like like a Gaussian ensemble for your random matrix. So you have this property, but like could have picked an ensemble, like there's like the Wishart ensemble where it's always positive definite probability 1. So how would you decide like
Right.
is there any like in practice like
we do. We're learning more about it. For sure. So this is what you get if you have real symmetric matrices with these conditions, as long as your variance is finite, and as n becomes large enough, it will do this. Okay. Right. So the condition here. Yes. One more question. No worries. The speak. Still here? Oh, it moved. Right. So you can kind of reason it here, right? So it's only as b is a negative number in this case, right? And so it's very far to the left. As I make b closer and closer to 0, this thing moves, and at some point it just joins the rest. Yeah, it joins the rest. And so that's why they're in here. There's just nothing special about this. Ultimately, there's nothing special about this direction, right? Okay. All right. So all right. So what to enforce this, we can simply draw a line somewhere. Okay, and this line would be something like this. Okay. And so this condition to have the matrix that is circled here be positive definite just means that you can't have any eigenvalues to the left of this, right? So in this case, I have all of these unstable modes. Everything else is stable, right? And so as you move this thing, or you change these the standard deviation of this matrix, you can make your you can change the number of unstable modes, right? And so the system is stable if you have nothing to the left of this line. So it does for because this thing is already diagonalized and everything on the diagonal is the same. So it just shifts the matrix. Yeah. No, it's not. It's a good question. Yeah. Okay. So that's the prediction, right? And so now we can think about with what this means. Okay. So I can't draw things in dimensions, but I can do 2. And we already did that last time. So I'll just draw again what this, like how we should be thinking about this. Right? If I only had 2, then this direction would be something like this. That's this direction, right? Which means that if I have this unstable mode down here, then it indicates right? It indicates the system wants to undergo large fluctuations in this direction, and so you should expect that you're going to get at least one condensed phase that is highly concentrated in all of your different polymeric species. Right? So that's what this direction means. You can have this orthogonal case, right, from something within the semicircle, which looks more like this, right? Which means that the polymer, like one polymer wants to get away from another polymer, right? The two, you should expect that the two types of phases that you get are going to be have similar phi1 plus phi2, but different amounts of each one. Right? So that's intuition that you can get. And just one more thing is that a very obvious way that you can make the system stable is just by reducing the overall polymer concentrations, because as you do that, you move this to the left. Right? Okay. Yeah. High concentration. It does, right? And so there's this approximation here, which we fixed here. You don't need to do this, right? You can keep this term here, right? And then this works everywhere in your space. But qualitatively, the picture looks very, very similar. At the end of the day, things mostly depend on the spectrum of the sets of interactions that you have. Right? And so what I want to emphasize is that it turns out that this assumption here is really the crucial one, right? Like if you say that everything is that all of your interactions are independent, then you get certain types of unstable modes with very little remaining information about the statistical distribution, right? As soon as you start adding in structure by saying that that there's actually like real chemistry involved, and certain polymers like to interact with certain binding partners, then you violate this, and this sort of picture in spirit still holds, but you need to think much more carefully about what sorts of distributions you have. Okay. Any other questions on that? All right, so what I'd like to do next is talk about how you can actually design certain phases, right? So let's suppose that instead of taking this statistical approach where we say the interactions are random and they're just given to us, can we actually design interactions in order to get specific phases? Yes.
The eigenvectors of that does that tell you the direction in which
It tells you the direction in which they initially start to undergo these large fluctuations. Ultimately, that doesn't have to be the phases where they end up, right? There is a strong correlation, and so computer simulations have shown that if you do all this properly without making these assumptions, and you introduce these random matrices, then indeed, sort of the initial direction of instabilities that you get, and also the number of instabilities that you get here, right? You're integrating over essentially a density of states. The number of instabilities is strongly correlated with the number of phases that you end up getting if it occurs through this sort of decomposition mechanism. All right. So question number 2. What I'd like to talk about is how complex do the biopolymers have to be? Right. So here, what we're going to do is think about sort of the opposite approach to what we had so far, where we're actually going to suppose that we start with some condensed phases, and we want to simplify the interactions, adding structure to these interaction matrices until we cannot do so any further, and that would be our simplest set of biopolymers that gives rise to some sort of set of condensed phases. Okay, so what we're going to do is assume that we have some condensed phases in coexistence with a dilute phase. And so what we've said before is that in order for this to work, we must have our equal chemical potential and equal pressure, osmotic pressure condition for each type of species and each of our phases, right? So we have K phases, so their alpha goes from 1 to K. Alpha equals 0 is our dilute phase. This is what we want to have. And a very useful way of thinking about this is to, yes. How many monomer types we're going to have, how long the chains need to be. What I want to get just for the moment is a condition on how you can relate perturbations to this interaction matrix, this epsilon tilde, to these sorts of things here. Okay. All right, so, and I think that'll become clear in just a moment. Okay, so to do this, what we need to establish is it's useful to draw a landscape that shows where these condensed phases lie. All right, so all right, so we're going to specify a system at constant chemical potential, and we can draw for a phase-separated system something that ends up looking like this. Right, this is our dilute phase, and this is one of our various condensed phases. Okay. Right, and so the way that you can get this is through this definition. So this is our thermodynamic definition of the grand potential. It's just the Helmholtz free energy minus chemical potential times its volume fraction. And this is something that we already know, right? We have our chemical potential calculated before for our mean field model. And we saw previously that this mu was something that looked, when we had phase separation, we had 3 crossings of x-axis. And so when we integrate, we get something that looks qualitatively like this. Right? Okay. Okay, so having our grand potential where we specify what the chemical potential is everywhere, and if we have the minima occurring at the same place, this satisfies equal pressures because at equilibrium, Helmholtz free energy minus mu times chemical potential, mu times volume fraction is just minus the pressure. Okay, so this is our starting point, right? What I'd like to do is simply ask the question, what happens if we take a system that's already phase separated and we make some very small changes to the interactions? What has to happen if I want to stay at phase coexistence? So the idea here is that I'm going to take my interactions and I'm going to perturb them to something that is epsilon plus delta epsilon. And I want to figure out how my grand potential changes. Okay, so to lowest order, I'm going to have variations in all 3 these things here, right? So I should have So to lowest order, this is what I have. Right? My free energy depends on the concentrations or volume fractions and these energies, right? And my chemical potential, the constant part here, and then the chemical potential itself can change if I make perturbations to these delta epsilons. Right? Okay, so this is my lowest order expansion. What you should notice is that this term and this term exactly cancel. Right? And so I get this answer to lowest order. Okay. And the last thing is I want to stay at phase coexistence, right? I'm making a small change to my set of interactions, which is going to perturb all my phases, but I want to make sure that I stay under the conditions where my phases are still in coexistence with one another, right? So that means that I need to maintain constant pressures, and that means that any change I make to the pressure in one phase has to be made to all the other phases, including the dilute phase. So I have to have this expression here. And if I'm going to use my Flory-Huggins expression, it's very easy to calculate this. This is just something that's quadratic in our sorry, the term that involves epsilons is quadratic in phis, right? So the final expression that we need is this is our final expression, right? Okay. Right, so we can interpret this. What does this mean? If we make some change to our interaction matrix, make some perturbation, it's going to need to be balanced by some change in the chemical potentials, and we can relate that to the change in concentrations in a condensed phase and the stability of the alpha phase. Okay, so if you have phases that are very stable, right? Small concentration fluctuations are restored very quickly and very easily, then you can make a large change to your interactions and still maintain roughly the same compositions in your phases, right? Yes. How do I get to this equation? So we have this one here, which leads to this. You also need to consider the fact that when you change epsilon, you also change mu, right? And if you put that all together and you set the change in your effectively your pressure in the two phases to be the same, they have to change together, then that leads to this final expression, right? But it's like a small perturbation times something that looks like a susceptibility gives you a response, or you can view it the other way around. Yeah. Yes? So delta epsilon is a matrix, right? We can perturb this matrix as long as we keep it symmetric. So these are vectors. This is a matrix, and then over here we have a vector matrix. Yeah. Yes. Yeah. So our yes, this has to be true for each of our alphas. Okay. All right. So the reason that this is useful is that it gives us a way of trying to change epsilon in order to modify the interactions between our polymers while keeping our keeping the polymer volume fractions as close to being the same as possible. Right? So the scheme is, if I already have a system that's phase separated, then I can make modifications to the polymer chemistry while still maintaining the compositions that I want, as long as I do things according to this equation. All right. So I can show you how this works in practice. All right. So this is very new, but I show this because I want to make it clear that even though we have this very simple description of polymer phase separation with the Flory-Huggins model, you can actually do quite complex things and really start to get at what types of polymers can give you very complex phase separated states. All right, so here's the basic idea. Let's suppose that I want to make this, right? I have different polymers. They go into different condensed phases, right? And this is my my target system, right? I can imagine that I want to either design some polymers, or I want to evolve some protein sequences in order to have this sort of phase separated architecture. Okay? And so again, in order for this to work, I have to have my equal chemical potentials for each of these species across all of these phases and the equal osmotic pressures. Right? Okay. So if I assume that I already have some epsilon matrix that would get this done, I can then adjust the chemical details of this polymer according to this equation, while maintaining a constraint that I don't change this as much. I change this as little as possible. So it gives me this rational way of doing this. Okay, right? And so it turns out that you can use this sort of scheme to optimize your polymers for sort of any property that you want. And I think one key thing is to look at how many monomer types you need in order to make complex phases. Right? The reason being that in biology you have a limited number of, say, different amino acid types, but if you string them together, you can get complex self-organization. Right? So how many of these monomer types do you really need? Okay, so that's what we want to do. The optimization here is directly just applying this equation and regularizing in such a way that we're trying to have the lowest or the fewest number of distinct monomers needed within this Flory-Huggins framework. All right. Okay, so just to convince you that this works, you can run molecular dynamic simulations of these polymers where we set up the system with two different condensed phases in contact and in contact with a dilute phase, and then ask whether, once this reaches equilibrium, whether it has the composition that we asked for, right? Were we in fact able to change the interactions between our polymers to reduce the number of monomer types while keeping the concentrations of the polymers in our different condensed phases the same as what we targeted in the first place. Right? And so to see that this works, you can introduce this order parameter, which just tells you how similar is my phase to how similar is the phase that I get here to the target that I had initially, right? So the goal was to build, say, phase one has these two molecules and phase two has these two, so we put them together, right? And this order parameter being one tells us that we have indeed maintained the compositions while reducing the complexity of these sequences, right? And again, complexity here now means that we're using the minimum number of distinct monomer-monomer interactions strung together into these polymers in order to get this clearly complex self-organized state. Right? Yes. So the epsilon ij's are the polymer-polymer interactions, right? So, but that is in this mean field framework an average over all the monomer-monomer contacts, right? So if you start by having a very large number of monomers and you start reducing that, then you necessarily have to introduce perturbations to that polymer-polymer interaction matrix. So that's this delta epsilon here. And we're trying to do that in a way that leads to the simplest possible epsilon matrix in terms of monomer types, while still maintaining these compositions. Yes, they're implicit in the epsilon matrix. Yeah, okay. So the take-home message is that you can make very complex phases from relatively simple polymers. Biology clearly does that. And I think we're starting to learn the rules by combining these random matrix approaches and more optimization-based design approaches to understand how all of this actually emerges. Oh. Any other question? Yeah.
So you show the semicircle law,
Mhm.
right? And that is an asymptotic result. So, it's true in the limit of infinitely large matrix.
Yes.
But this thing has how many interactions? Like 3, 4 maybe?
Right. So this is a simple example to be able to show. You can take this and go to many more species and many more monomer types, polymer types, et cetera. The key distinction between the random approach and this sort of approach is that in the random one, we have this assumption that all of the interactions are uncorrelated with each other, right? Which, if you think about how you'd actually do that in terms of biochemistry, it's actually very difficult, right? But if I have a particular monomer that interacts in a particular way with another monomer, then that's going to provide constraints on how it interacts with other things in the system because there are only so many types of physical interactions, right? So one could argue that initial assumption was a bit unrealistic. And if you instead go all the way to this other limit where you say, I'm going to come at it from the point of view of I can design everything optimally, right? Saying, evolution has found the perfect solution, then what can I possibly do? And I think biology is somewhere in the middle. Sorry. I'm sorry, one more time.
How
Yes.
do you-
How do I define it? Okay, yes. So here, this is just general. This is just our Flory-Huggins. We're saying that the overall interactions between our polymers are these are given by these, right? But we have to say what this matrix is in order to say something useful about multi-component systems, right? And so these are two limiting opposing approaches. One where you assume nothing except a statistical distribution, and the other one where you assume that you can optimize the heck out of it, right? And you can just do whatever you want, right? And when you take an optimization approach, you are introducing lots of structure into the matrix, right? The structure here being that you have a small number of monomer types. So that means that the way the polymers interact is not at all uncorrelated. It's determined by the monomer interactions. And so that is sort of opposed to this picture. Okay? And like I said, I think that biology is somewhere in the middle.
So are you saying that you start with an initial composition in phase space, and then you're tweaking epsilon such that whatever it phase separates into is something that's controlled by? Is that what?
Right. So what's being optimized is these chains, right? These polymer sequences. Right? So I'm trying to choose these sequences, right? Such that the interactions between these beads and between the polymers overall gives rise to precisely the phase-separated organization that I asked for in the first place. Right? So it's an optimization problem because I'm imposing the phases that I want to have, right? And then I am trying to do two things. I'm minimizing the complexity of my polymers by reducing the number of monomers while satisfying this constraint. Right? Because in general, if I start just playing with the different monomers, the compositions of the phases will change, and I don't want that to happen, right? So I need to minimize this thing here. Effectively, it's small. This is small. Marcus.
One is, I want a certain number of phases with respect. You could ask, well, how many different polymer types or p-types are used for that? Second question is exactly what p-types would then actually do that.
Yes.
And for the first question, there must be something for like this close to protein architect. The second one is very complicated to actually tell find the value. So you ask the second question.
It's actually both, right? Because it's not a simple, like the number of phases that you can have, sure. If you Gibbs phase rule tells you a lot about that. But the question of how complex do the interactions, or like what sort of, more specifically, what structure does my epsilon matrix have to have in order to make that happen? That is actually a complex optimization problem. Okay, so yeah, another question. Right, so the free energy is you can get it from integrating the chemical potential that we had, right? And so if in our Flory-Huggins mean field approach, we have our epsilon ij matrix that tells us how the polymers interact, right? And so that is precisely the derivative that shows up here. Mhm. Yes, yes, yeah. All right. All right, great. Okay, so for the last, I guess 30 minutes or so, I'd like to talk about interfaces between different condensates. And let's see. We put this up just for a moment. All right, so we'd like to go a step farther, and even up to this point, even with our multi-component systems, we're still thinking in terms of just bulk phases, bulk phase diagrams. And what we'd like to describe is how you can attack interfaces. So interfaces here can either be between different fluid phases, different condensate phases, or between condensates and solid substrates. Solid substrates, for example, DNA or microtubules inside the cell. Right? So we have lots of possible interactions here. The framework that we're going to use is best motivated just by considering going back to our single polymer system, right? So we have, you can imagine our condensed phase here. Our dilute phase here. Right? So if we go far in this direction, we have one of our bulk phases. This would be the one that has very low polymer volume fraction. If we go in this direction, we have our condensed phase with a high polymer volume fraction. Right? So can we use this free energy framework that we've been talking about so far to describe something that is now varying continually in space? Okay, so the basic idea, and I think a lot of this was actually dovetails quite nicely with what Marcus was talking about yesterday. We can consider an expansion in terms of derivatives with respect to this one-dimensional spatial coordinate. So we can start with just one-dimensional system and Z here. And we can define a length scale that depends on how rapidly the polymer concentrations are varying in space. Okay, and so what we're going to assume is that this is much less than some intrinsic correlation length. Right? Or in other words, any sort of spatial variation that's happening here is happening over a very long wavelength compared to the correlations that you get in between the polymers in your bulk system. Right? So the easiest way to think about this is to imagine that I look in my fluid and I have, say, one polymer here, another polymer here. How far do I have to go from the center of one to have no information about the chance of finding another polymer, right? So if I go very, very far away, then the probability of finding another polymer chain is just going to be given by the average polymer concentration, right? And so there's some intrinsic length scale here that's definitely bigger than an individual chain, but on length scales much larger than that, we can safely define an equilibrium free energy using the techniques we already described. Right? So we want things that vary slowly in space. Again, this thing here has to be much larger than, our length scale has to be much larger than the size of an individual polymer to do this. Okay. So the basic idea is that if we now have something that is spatially varying, we want to write down a free energy functional that describes how the free energy depends not only on the bulk concentration rho, but also on these derivatives with respect to spatial coordinates. So this is going to look like this, right? So we have a total free energy here. We have our free energy density here. And we can do an expansion in powers of this inverse correlation length. Okay, right. So according to this, here this is like 1 over the correlation length. It's like 1 over the correlation length squared. We have higher order terms, and we ignore those. Yes. We are expanding around our bulk density here, right? So this bulk density would be the one where you have no spatial variations at all, which would say that this length is infinite. In general, right? So we're expanding around F naught at some particular rho, right? So this is a function of rho, right? So this expression should be true for any rho with then spatial variations around it. All right, so we can look at these terms. And the first thing to note is that this one here is problematic. Right? The reason being that if I were to just take my picture here and flip it around or look at it from the other side, I would change the sign of the derivative with respect to z, right? And that shouldn't change the physics, right? So this bisymmetry just cannot be here. All right. Right, so I'm left only with these two terms that go like 1 over my correlation length squared. Okay, so let's look at this one here. So for our second 1 over correlation length squared term, we have something that we can integrate by parts. And we have our boundary term. Okay. Our boundary term can be neglected because we can safely assume that if we, in general, if we go very, very far away to plus and minus infinity, then we can assume that there are no spatial variations. All right, so we can drop this. And then the second one can be integrated into some new constant some new F2 times squared, right? And so if we do, what's that? The minus sign. Yes. Well, yes and no, right? This is some new definition. Like I could have wrapped it up, but we can do that. Yeah. Okay. And if we do this, we get our final result here. So this is what's called the square gradient functional. Again, can show what these terms mean, right? So this is something that depends on your rho as a function of z, so the spatial distribution of the polymer in the system. We have two contributions here. One is this bulk free energy density, which is evaluated at rho. And then you have something here, which is our square gradient. And this increases the free energy whenever you have spatial variations, right? So it therefore makes sense that this is a positive contribution, right? So in general, we haven't actually said anything about what this F2 is, right? But we can go ahead and treat it just as a constant for simplicity, right?
F2 is the same F2 of the whole equation, right?
This one is now the sum of this one and this one, because we ended up with two terms that both go like the square gradient. Okay, so right, it turns out that for mean field models, such as the Flory-Huggins model, you can actually show that this is precisely a constant, right? That this thing is independent of the variations in rho, right? In general, for example, the associating polymer model that we considered, this thing should not be treated as a constant, but it's customary to make this assumption because it makes life a lot easier. Right? So we're going to treat this as a constant, which is positive, and again, it acts to penalize these variations in the polymer concentration throughout space. Okay. Yes.
why it makes sense to treat it as a constant, or is it just a useful simplifying assumption?
Right. So in certain models, it falls out as being a constant, right? So for the Flory-Huggins model, this is a constant. In general, it is not, but it is often treated as one. And in the sense that any variation of this would effectively be like higher order terms that we've been neglecting. Yeah. Okay. This has to be positive for physical reasons, right? So again, these various F2s that came out just by showing that both of these second order terms can be grouped into one, I wouldn't worry about those so much. The key thing is what is this final number? And I want to spend a few minutes talking about how you can actually interpret this thing. But the key thing to notice is that it absolutely must be positive, because otherwise you would lower the free energy by creating variations. So if I started with a bulk phase that was homogeneous and I started to introduce spatial variations, then that would drive the free energy lower, and clearly that's nonsensical. Yes, but there is a bit more, I think, useful way of trying to figure out what these values are, right? There's a microscopic way and a macroscopic way. Microscopically, you can say that this is the sort of functional I'm going to work with and match the variations that you get at long wavelengths to what you'd get from a statistical mechanical description of, say, this polymeric system. And you can do that. It's quite complicated. The other thing that you can do is to take a macroscopic description where you just simply say, okay, I want this to match some bulk interfacial properties. And if I do that, then I can fix this value without really ever worrying exactly about where it came from. It just becomes something that's a fitting constant for matching macroscopic properties. Okay. All right, so we have this. Okay. In our system, here we have a system at equilibrium, right? Which means that the polymer should not be moving, right? Which means that we must have constant chemical potential throughout, right? This is no longer a statement of constant chemical potential between two phases, but now a statement of constant chemical potential absolutely everywhere, but for the same reason. So for that reason, we should, again, use this grand canonical ensemble. And so we get a new functional. Right? So mu is a constant everywhere. This is just the definition of our grand potential. And this is the thing that we should be minimizing if we are going to find equilibrium. So we want to minimize this functional with respect to rho. And so that entails an Euler-Lagrange equation. So you take the functional derivative of this with respect to rho, and you set it equal to 0, then this is the equation that you get. Um, and it's a bit more, it's a bit more natural to, again, use this grand canonical description. Again, F minus mu times concentration is grand potential, right? So we can define a grand potential density. If we do this, we get okay. So to go from this line to this line, all we've done is substituted in this definition of our grand potential. We've applied the boundary condition that if I go very, very far away, where there's no variation in the polymer concentration spatially, then my grand potential must be always minus the pressure, right? So if this thing is 0, then P equals minus omega. And then we just integrate it to go from here to here. So what you might notice is that this looks exactly like conservation of energy in mechanics, right? We have something that looks kind of like a velocity squared times some coefficient, and this thing here is acting as our energy, as our potential energy. Okay. What's useful about this equation is that this is our equilibrium condition. And it tells us that the contribution to our free energy up here is going to be balanced, right? We have an equal contribution from the part having to do with the bulk chemical potential difference, the omega minus P, and this contribution here, which was our square gradient term. So the lowest free energy state, the one that's going to minimize our profile, is always going to be the one that has equal contributions to the free energy from two different sources. One, from the fact that to have an interface, you need to have in this region here, we have to have intermediate values of rho, intermediate polymer concentrations that are somewhere between the very happy condensed and dilute phases, right? And so the more that we can shrink this region of space here where we have this interface, the more we can reduce that contribution to the free energy. But doing so comes at a cost that we have to add a higher gradient in this portion here, right? So these are two competing effects, and the competing effects are equal at the point where we minimize the grand potential. Yeah.
I don't know if it's for plugins, but if I put a different model, you might not get that.
Domain wall meaning a very sharp interface? Well, so there's a variation, right? And so there are to that two key points. One is that we have assumed that that we only keep terms up to this point, which means we can't have undulations that are have correlation lengths comparable to the true like polymer length scales. They have to be long, right? But the other thing is that it's going to depend on what this F2 is here, right? If you had, even in this model, with that assumption, if you have no penalty for forming an interface by making this 0, then indeed you would just have a step function. Okay, so it turns out that this is really all you need in order to be able to describe quite a lot of phenomena. And so here, we are considering only, say, 2 phases that are taking up all of space. We can do other things. We can add surfaces, substrates with different boundary conditions. This thing is always going to hold in the bulk, right? This equilibrium condition is always going to hold, but the precise sorts of phenomena that we see are going to depend on this. So can I just show a couple more pictures and then wrap up? Okay. All right. So the reason that this is all so important is that I hope that I haven't misled too much by focusing so much on bulk properties of these phase-separated biopolymers. Of course, if you take most biopolymers and reconstitute these systems in vitro, you can get truly macroscopic phase separation that looks just like phase separation you'd have for inanimate systems. Right? But inside of living cells, phase-separated droplets are typically much, much smaller and are interacting very strongly with their environment. And in many possible ways, I think some of the most interesting being interacting with surfaces such as DNA and microtubules. So you can use this theoretical framework to describe this sort of behavior by adding in appropriate boundary conditions. So what we have here in this example, we have a piece of double-stranded DNA that is being pulled apart by 2 beads in optical traps. And there is a polymer that can undergo phase separation in bulk in the surrounding solution. And the key thing is that at physiological concentrations, you don't see gigantic droplets forming. Instead, what you have is interactions between these polymers and the DNA, in this case through transcription factors, which lead to the formation of these very small droplet-like structures. Right? But this is actually all taking place outside of the binodal, outside of the region of the phase diagram where you'd form macroscopic droplets. Right? So I think in order to be able to think about these sorts of scenarios, you really need to take into account these interfaces and think about not just the polymer-polymer interactions in the bulk, but also the polymer interactions with various substrates. Another really beautiful example comes from this work on microtubules that form bundles in order to make the mitotic spindle for cell division. And again, what happens is that you get these droplets that form on the surface of these microtubules. They initially form a full layer, and then these droplets split over time due to the effects of surface tension. And again, all of this has been described quite beautifully in terms of this square gradient functional framework, which can help to explain why systems like this are stable even when you don't have macroscopic phase separation. Right. And one last example, just because I promised to make some connection between bulk phase separation and membranes. It's possible to have polymers in bulk that can interact with proteins that are embedded in membranes. And if both of these systems can undergo phase separation in the membrane into this is a surface phase transition, and in bulk we have a three-dimensional phase transition. If these two things can interact, then it can actually dramatically affect the overall phase diagram. Importantly, you can get phase separation in the bulk under conditions where it would never occur if you didn't have this fluctuating surface nearby. Right? So appealing back to our sort of Flory-Huggins description, we can have bulk coexistence where if you only had polymer in bulk with no surface nearby, you would only have phase separation if you were in this yellow shaded region. But with the ability to have coupled fluctuations between the bulk and phase separation on the surface, you can extend this region and get this coupled surface bulk phase transition. Okay, and again, all of this has been described quite beautifully in terms of this square gradient free energy framework. All right. Okay, so I think my time is up. In just a few words, key takeaways, what I hope that you've gotten out of this is that polymer theories can explain many of the qualitative features of near equilibrium phase behavior. Cells are not necessarily at equilibrium. We know that they're not, but a lot of these sort of qualitative features can be understood in this language. Having long polymers is essential, but predicting what exactly happens, particularly from sequences, is a major challenge in this field, and there are many people working on this. Because sort of the qualitative picture that I've given you is not enough to be able to say specifically what happens for different biopolymeric systems. In multi-component systems, you can have very complex self-organization. Somewhat surprisingly, this can happen even if you have relatively simple building blocks to work with. And interesting condensate biophysics happens at interfaces. I think the most interesting biology happens at interfaces. So thank you all so much for your attention, and let me know if you have further questions.
They'll be around until the end of the week, but Friday.